Chapter 7.5 has a lot of complicated math associated with the derivation of these theories. But luckily, as complicated as the math is going to be, you don't have to really get into the calculus-based understanding of this in order to get what we need to out of this chapter. It's all based around this idea of the Schrödinger wave equation and the Hamiltonian operator that defines the energy levels that are associated with each electron. Now remember, each electron has its own set of energy levels that's associated with its wave properties, right? Because waves have energy, particles have a velocity and that sort of thing. So there's kind of a kinetic and potential energy associated with these. Well, the particular wave function, the little symbol psi here, Greek symbol psi, represents the wave function of the electron, kind of its wave properties. And the energy of that particular wave function can be derived from operating something called the Hamiltonian operator on the wave function. That's kind of like saying you're going to take an average of something. What are you doing? You're applying a mathematical set of formulas to a data set and ending up with a solution. If you're going to take a derivative, if you're into calculus, you apply a certain methodology to an equation, and the result is another equation. The Hamiltonian operator has the same kind of idea, although the math degenerates rather quickly in terms of what you actually need to do to operate this Hamiltonian on a wave function, which isn't even all that simplistic a formula to begin with. But in any case, what do we need to know? What you need to know is when the solutions are made and the solutions are found for that particular intensely complicated equation, you get a couple of constants that fall out of that define energy levels for electrons and the probability of finding them in a certain space relative to the nucleus. So those constants are labeled n, which is the principal quantum number, L, lowercase l here, which is the angular momentum quantum number, m sub L, the magnetic quantum number, and then on top of that you have this fourth constant, m sub s, which defines something called the electron spin quantum number. Now, alright, so L actually should be n minus 1 here, a little correction on the slide. But in any case, n, the principal quantum number, can be any integer greater than 0. So we're talking about 1, 2, 3, 4, etc. And this really corresponds to the primary distance, how far away from the nucleus the electron will be found at. And as you make larger and larger values of the principal quantum number, we're getting farther and farther away from the nucleus. Now L can be any integer from 0 until 1 minus, or n minus 1, so 1 less than n. So when n equals 1, n minus 1 equals to 0, so we can be from 0 to 0, which basically means L can only be 0. Now if n equals to 2, 2 minus 1 is 1, so L can be 0 or 1. For n equals to 3, we have 3 minus 1 is n minus 1 or 2, so we can have 0, 1, or 2 be the value for L, and so on. What this corresponds to is kind of the shape of the electron orbital at that particular distance away from the electron. So at n equals to 1, we have only the 0 possibility, meaning that we really only have one possible shape that we can find for orbits of electrons at this distance away from the nucleus. Now at n equals to 2, we can have the 0 shape, or we can have the 1 shape. So there's two possible shapes that can exist at this particular distance. It's a little farther away. We can have more shapes associated with how an electron can occupy space at that particular distance, and so on. Now these letters, letter L constants, are sometimes given letters to make them a little bit easier to differentiate when we talk about them. So 0 is given S or S-shaped orbitals, and 1 is given designation P for P-shaped or D-shaped or F-shaped orbitals. And that's kind of the slightly easier way to talk about these things. And we'll get to that later, but for now we'll keep to L equals to 0, 1, 2, and 3. Now M sub L can be any integer from negative L to positive L. And what these really kind of refer to is the orientation in space of that particular shape. And L equal to 0 means that M sub L can only be 0, from negative 0 to positive 0, right? So still just 0. So that means that the L shape, L shape can only really have one orientation in space. And what we'll see in the next section is that this is actually a sphere. So a sphere really only has one orientation in a three-dimensional space. Now at L equals to 1, then M sub L can be from negative to positive L, and everything in between, that is integers. So negative 1, 0, and 1. That means we have three orientations in space. And we'll look at what those three orientations are in the next section. Then the same thing, L equals 2, 5 different possibilities. L equals to 3, 7 different possibilities, and so on. We really don't have anything above L equals to 3. We don't have any atoms that really have a designation of larger than that, at least not anything stable. So we're going to limit ourselves to L from 0 to 3 here. Now M sub s, the quantum spin number for the electron, can either be plus 1/2 or minus 1/2 for electrons. Alright, so yeah, but what do you really need to know about this stuff, right? Well, what you need to know is that an electron basically gets an address of where it is in space in terms of exactly where it's occupying. And we can only have one electron for each unique set of quantum numbers, so each location in space. So we have to kind of build up a series of these numbers starting from the lowest possible combination, and that will designate where in space we are actually likely to find the electrons. So let's look at hydrogen. Its lowest n value would be 1. That's the lowest value we can have for n, right? It's 1 and 2 and 3. It's integers that start with 1. So the electron for hydrogen would be at n equals to 1. Well, if I have n equals to 1, what could the other values for the constants be? Well, n equals to 1 means that L can be from 0 to n minus 1. So 1 minus 1 is 0. So the only thing L could be is 0, or the S shape. Okay, so M sub L is from negative L to positive L. So there's only 0 for that one too. And M sub S can be plus 1/2 or minus 1/2. Let's start with the plus 1/2. Minus 1/2 will be if we run out of other possibilities. Okay, so helium has 2 electrons. So where do they reside? What's their address in space? Well, n sub 1, L equals 0, M sub L equals 0, M sub S equals 1/2. That was hydrogen's first electron, and it's also helium's first electron as well. Okay, well, where's the second one? Well, we still have another possibility for n equals to 1. We only have one possibility for L and M sub L, so those stay both at 0. But M sub S can be plus 1/2 or minus 1/2, so that's where the second electron resides. Okay, so we have one electron and a second electron, and they're both in this first distance away from the nucleus. Alright, the third, we run out of the third element, lithium, we run out of n equals to 1 orbitals. Okay, well, where does that third one go then? Well, the first two go into the same places as we just had for the hydrogen's first atom and then lithium's 2 atoms. So the third one we have to push into n equals 2. Well, n equals 2, we have a couple of possibilities for L. L can be 0 or 1. So let's start with the lowest one, L equals to 0. So M sub L only has one possible value, negative L to positive L, so 0 to 0. And M sub S, plus 1/2 or minus 1/2, so we'll start with the plus 1/2 again. Notice something here. N equals to 1 is one distance away. N equals to 2 is a little farther out. These are the core electrons that we talked about earlier. That helium has a full shell of electrons, and that shell is that principal quantum number, n equals to 1. Once we move into the second row of the periodic table, we're in a new distance, a new shell, the one that can hold 8 possible electrons instead of the 2 that the first row can hold. And that 2, n equals to 2, designates that farther out distance. And now this is the valence set of orbitals for this set of elements, the second row's set of elements. Okay, so 2 core and 1 valence electron, just like we know lithium has, except now we know the address of it. We know where it is in space. I have lithium a second time for some reason. Oh, I just put this in here so that we have a permanent record of where that address is. Excellent. So beryllium, same kind of idea, right? We have these are the same as lithium. Now we need another possibility for that second electron in the valence orbitals. So we still have the core electrons at n equals 1. And now we have 2 valence electrons at n equals 2. So they're the plus 1/2 and the minus 1/2 for the n2 m sub l l0 set. And we can keep going with this. We'll add on another one. This is the third electron into that valence shell, or the 5th one for boron. And now we are no longer having the L equals 0 ones. That's the S shape, or the S designation. L equals 0 is S. So now we're in L equals to 1, which is the P set of orbitals. And we'll start with L being 1, designates m sub l, -1, 0, or 1, so we'll pick the lowest of those, -1, and then we'll start with m sub s equals plus 1. Okay, so this is the 5 electrons of boron. And you can kind of continue this pattern and say that you have core electrons for carbon, we have 4 valence electrons for carbon, 2 of which are in an S-type L value, and 2 now are in a P-type orbital shape, but they're still the same basic distance for the valence orbitals, meaning that they're all still counted when they bump into something. That's why there's 4 valence electrons, and there they are. And nitrogen, same kind of thing. We're just changing the orientation of these p orbitals. Right? So -1's orientation, same shape, 0's orientation, +1's orientation. So they're all still p-type orbitals, and we're kind of giving them symmetric spins here, +1/2 for each. Well, you can do this, and you can kind of continue the pattern. Now that we have 3 of the p orbitals, we go back to the same orientation, but a different spin. Same orientation as we've covered previously, but a different spin, -1/2 versus +1/2, until we get to neon. Now we have core electrons, valence electrons. How many do we have? 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 total electrons. There's that full outermost valence shell, right? 2 of them in an S shape orbital, 6 of them in a P-shaped orbital, and 3 different orientations and 2 different spins, 2 different spins for each orientation. Yeah, there's got to be a better way than this, right? Than just listing off all these complicated addresses. It's like going on the internet and typing in the IP address every time you want to go to Google. Right? Just not the easiest way to do something. So instead, we can kind of separate these things out. At n equals to 1, we have the S-shaped ones with m sub l equals to 0. And then we can draw an upward arrow and a downward arrow to indicate +1/2, or a downward arrow to indicate -1/2 for m sub s. And then at the second quantum level, n equals to 2, we have the L equals 0 and the L equals 1 shape, which is P, so 2s, 2 being the n value, 2s or 2p. We have one possibility with 2 different spins. And then we have 3 different orientations in space for the 2 p's with 2 different spin possibilities as well, plus 1/2 and minus 1/2. And then we get to the d's with 5 possibilities. Each can have 2 different spins worth of electrons. So you can kind of organize things a little bit easier like this than having to write out a set of 4 numbers every time you want to try and designate what it is that you're doing. So let's look at hydrogen again. So 1s, upward arrow, 1 is N, L is 0 because it's S, M sub L, there's only one possibility, so we only draw one line to designate one orbital orientation, and M sub S, upward arrow, so plus 1/2. Okay. Helium, again, 1s, line indicates 1 M sub L value, N equals to 1, L is S, so L equals to 0. Now we have 2 electrons, so plus 1/2 and minus 1/2. Excellent. So lithium, we have the same kind of idea, except now we have the 1s plus 1/2 and minus 1/2. We have the 2s for the third electron, so we have N equals to 2, L equals to 0, 1 orientation in space, and plus 1/2, meaning up arrow. All right. Let's skip ahead to carbon here so we can see how this works. 1s, 2s, and 2p. So here we're drawing the 2s, which is 1 possible L, 1 possible orientation, and the 2p have 3 possible orientations, -1, 0, and plus 1. So we designate that with 3 different lines. Okay? So when we draw this, we're going to have 1s, 2s, and 2p. And we can kind of think of this as the 3 M sub L designations. So carbon has 6 electrons altogether. So 1, 2, 3, 4, 5, 6. Excellent. So you can see too, here are the 4 valence electrons farther out, second level, and here's the 2 core electrons. Now if we skip ahead to neon and draw out the same configuration, and we have 10 electrons altogether. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Voila. So how does this work with the periodic table? Well, you can look at the periodic table and you can kind of see where these different designations fall. N's principal quantum number on the periodic table corresponds to the row. Right? And where we'll find these different electrons. So the first row only has N equals to 1. The second row has everything before it, so N equals 1 and N equals 2. Third row, N equals 3, etc. as we go across. Well, this first set, we have L equals to 0. So M sub, that's the S shape. And we have 2 electrons that can fall in that. Helium, you can kind of think of as being right here for that designation. So N equals 1, L equals to 0, 1 electron, 2 electrons in that particular 1s energy level. And for N equals 2, now we have the 1s and the other 1s, and now we have the 2s, because these two columns are the s designation electrons. So lithium has n equals to 2, first two columns, so s designation, and that's where we'd find that electron. Beryllium has the second one, so that's 4 electrons total. Hydrogen, helium, lithium, beryllium. And now when we go across to boron, these 6 elements correspond to the 6 possible electrons that can go into these 3 2p orbits. Right? So this section is the L equals to 1. Remember, for this consideration, we put helium here because it's a noble gas, but electron-wise, it's really over there in that second column. But these sets are the L equals to 1, or the p-shaped orbitals. So boron would have the 1 electron. Carbon would have a second one at L equals to 1, or 2p. A third one for nitrogen, a fourth for oxygen, a fifth for fluorine, and a full valence shell now for neon. Okay? So all we have to kind of do is look at the periodic table and kind of see how this is laid out. And we can kind of notice also in here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Remember, the L equal to 2 shape has 5 different possibilities for orientation in space. And I said L equals 2 is the D designation shape for orbitals. So if we have 5 different orientations in space, for 3D, we have -2, -1, 0, 1, and 2. There's 10 elements across this row, because we can put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons in that particular set of orbitals. That's where the 10 elements across the middle come in terms of how they're organized. So now we can kind of see that not only does the number of valence electrons start to designate what the properties of that particular column's elements will have, but that ones in the same column with each other, like beryllium, magnesium, and calcium, have their final electron in the same shaped orbital. Okay? So in this case, the second electron in a S-shaped orbital. 2s for beryllium, 3s for magnesium, and 4s for calcium, respectively. So in the next section, we're going to talk about what these shapes actually look like and start to designate a little bit more what these shapes mean in terms of reactivity.